Welcome to the lecture series on numerical methods, finite difference approach. In this lecture series, in the last lecture we have discussed elliptic equations and their solution procedure based on like explicit approach and implicit approach. And in this lecture we will discuss about this alternating direction implicit method for elliptic equations. So, if you will just go for this ADI method here for elliptic equation. So, alternating direction implicit method especially, that is considers this sum of the steps calculation, like in the x direction we can just consider like a half step calculation, and in the y direction we can just consider another half step calculation. So, to solve this elliptic equation, if you will just use whatever we have just discussed in the previous lectures for this parabolic equations especially. There we have just considered that if we are just considering this direction of x movement in the n plus 1 steps, and then we are just considering like y direction movement in n plus 2 steps. Then further we are just considering this x in the n plus 2 steps and y in the n plus 3 steps there. So, likewise we are just combining the steps for this calculation of values or variables at different points. So, in this method if we want to solve like elliptic equations, so same approach can be employed with some modifications as time steps are replaced by iterations here. So, suppose if you will just consider a general elliptic equation that is in the form of like del square u by del x square plus del square u by del y square minus alpha u, this equals to f of x y, where alpha greater than 0, and which is defined over a domain. Suppose x lies between 0 to a and y lies between 0 to b. If you will just see here the domain, if you will just define, this can be the domain, since this is the y direction here, this is the x direction, and starting point x equals to 0 here, and x equals to a here, and y equals to 0, then y equals to b here. So, since the boundary conditions, it will be prescribed at these values there and these values here. So, that is why we will start x equals to 0 here, then we will just start at x equals to 1 to x equals to n minus 1. If you will just divide this domain into, suppose like in the x direction, if you will just divide into m grids, and in the n direction if you will just subdivide into n grids here. So, this is suppose m direction here, sorry, in the x direction we are just subdividing into m dividends or m divisions. Then our calculation will vary from like 1 to m minus 1, and j will vary from 1 to n minus 1. And if this like step size is considered as h here, so then we can just divide this domain in the form like this one here. So, h is each of the space size or the grid length space here, and if we will just consider the same space size in the y direction also, then we can just consider this is just the h size for each of this grid lengths, and then the total length can be determined as like total length we can just write, that is as a minus 0, this is equals to m h, since h represents here the small grid length there, since m parts it has been subdivided. So, the total length can be written as m h there. And if you will just move in the y direction, same can be considered, that means that in the y direction total division is n here, and the each of these small grid size is like h. So, nh, this can be written as the total length, that is b minus 0 equals to b there. So, that is why we have just written here nh equals to b and mh equals to a here, and we have to determine uij at each of these grid points here, which is not known to us. So, if you will just go for this discretization of this equation, that it is just represented here in the form like del square u by del x square plus del square u by del y square minus alpha u, this equals to f of x y for alpha greater than equal to 0. So, if you will just use the central difference approximation del square u by del x square, this can be written in the form of like ui minus 1 j minus 2 ui j plus ui plus 1 j by del x square, or you can just write by h square here. So, then if you just discretize this equation here, this can be written in the form of u I j minus 1 minus 2 u I j plus u I j plus 1 by del y square. This is the complete representation of del square u by del y square. And since alpha is there, so u is defined at I j grid points, or at the I j grid points we are discretizing this total partial differential equation. So, that is why this point is written as u I j there, and the last point it is just written as a f of x y. So, that is why this can be defined at x I and y j point there. Since your del x square is h square and del y square is h square, so we can just write it in a modified form that h square can be taken and multiplied at this numerator side here, that is in the form of alpha h square u I j, and this is h square f I j here. Suppose the value of u is known at the nth iteration. Previous iteration it should be known to us, or initial guess we can just provide all these values either in the form, if it is just provided then we can just write that values, and if it is not known to us at the beginning we can just consider that values as 0, and we can start the iteration, and each of this iteration we can just consider this previous iterated value, it should be known to us. Hence, the term containing u here, it can be broken into two equal parts. So, one part can be used for current iteration and other can be used for previous iteration. Let we are just using here ADI scheme with successive over relaxation method or successive under relaxation method. Since in the earlier formulation we are just independently using this ADI method without using SOR method there, but here we tried to implement SOR method in a combined form with this ADI scheme to get an improved solution. So, suppose rho be the relaxation parameter, then ADI scheme will be applied from nth iteration to n plus 1th iteration first, then followed n plus 1th to n plus 2th iteration in the following manner that we have just written here. At the first stage we write the term corresponding to del square u by del x square, since this movement in the x direction here, for n plus 1th iteration, and corresponding to del square y u by del y square for nth iteration, and the term containing or corresponding to u I j is written as, since two parts we are just subdividing, so that is why you can just write as half u I j plus half u I j, where first half of u I j can be considered at nth iteration and the other half it can be considered at n plus 1th iteration. So, if you just subdivide it in this form, then we can just obtain this complete equation as in the form, since if you just see here rho is multiplied there. So, u I minus 1 j n plus 1, since x we are just considering, since del square u by del x square term we will just consider at n plus 1th step, and del square u by del y square we will just consider at nth step there. So, that is why this nth step calculation, if you will just see, this contains all of these terms which is involving with the y discretization terms. So, that is why if you will just see here, so u I minus 1 j, so minus 2 u I j plus u I plus 1 j n plus 1, plus if you will just say here that we are just written that minus alpha h square u I j minus alpha h square u I j. So, which is written in the form of half of u I j plus u I j, and half portion it is just at n plus 1 level, half it will be at nth level. So, that is why it can be written as like alpha by 2, since alpha is multiplied there, into h square u I j to the power n plus 1, and here also alpha by 2 h square u I j to the power n plus 1 n here. And last factor if you will just see here, that is as h square f I j, it is just additive there, but we have just added, if you will just see here, rho u I j to the power n plus 1 and rho u I j to the power n to get it updated from this SOR method there. So, at second stage from n plus 1th iteration to n plus 2th iteration, the terms corresponding to del square u by del x square is taken at n plus 1th step and corresponding to del square u by del y square at n plus 2th iteration. Since function is dependent on these independent points or at that point itself, that will take the functional value. So, that is why this will not get changed. Here if you just see our j is varying from 1 to n minus 1 and I is varying from 1 to m minus 1. Since these equations will be used for computation of the values at the unknown grid points. Since we are just using SOR method here, we have to use this relaxation parameter for these equations. So, especially in the last lecture we have discussed about successive over relaxation method, where this relaxation parameter especially it is used for higher grid sizes as in the form of half alpha h square plus 4 sin square pi by 2 r into half alpha h square plus 4 cos square pi by 2 r whole to the power half, where r can be considered as a maximum of m and n there, and always we will just consider rho is positive and its optimum value for maximum rate of convergence, it can be obtained from this equation here. So, this method can be applicable when we will just consider rho equals to 0. If we will just consider rho equals to 0 in this equation, so directly we can just write that one as the ADI scheme there itself. So, that is our general ADI scheme. We are just considering here this problem, which is a semicircular domain or irregular grid points can be chosen to find the solution. So, for this Poisson equation, the problem is given like del square u by del x square plus del square u by del y square, this equals to f of x y is defined over a semicircular domain enclosed by the circle x square plus y square, this equals to 0.25, and x axis with f of x y equals to 4 into mod of x plus y. The boundary conditions prescribed on the circle is u equals to 1 on the x axis del u by del y equals to 0. So, since the problem is asked that we are just writing this equation that is in the form of nabla square u equals to f of x y, and above this is semicircular domain we are just assuming u equals to 1 here, and along x axis we are just considering this as a del u by del y equals to 0 there. So, if you will just subdivide this domain into square mesh by drawing suppose the parallel lines to along the y axis through x equals to minus 0.25, 0 and 0.25. Since this defines the circle with a center at origin, this is like minus your equation is varying from 0.25. So, this is just taken in the form of 0.25 then 0.25. So, that is why this final point will be 0.5 here, this will be 0.5 here. And if you will just consider here, that is the domains is subdivided into two different lines drawn along the y axis through x equals to minus 0.25 here and x equals to 0.25 here, and one more line it is just plotted at y equals to 0.25 here. So, then we will have regions 1, 2, 3, 4, 5, 6, 7, 8 here. But since the center line symmetry it is just used for this problem. So, if you just calculate 1/2 of this domain here, so other half we can just consider as the symmetry condition there itself. This problem is symmetric about y axis. So, we need to have to find the solution in the quarter of the circle at the mesh points. If you just see here, that is at 1, 2, 3, 4. So, this point, this point, this point and this point here. Since this value is known, u equals to 1 here, u equals to 1 here, u equals to, sorry, this is your derivative boundary condition, it is just given here along this line here, and this point can be considered as the symmetricity. So, that is why one point can be taken from this point. So, if you will just go for this calculation of this problem here, then we can just find that first we have to solve to get the sides B4 equals to C4 there. So, if you just put like x equals to 0.25 here at that grid point, if you just start computation of this domain here, so it is just given that this domain is subdivided into two parallel lines, x equals to minus 0.25 and x equals to 0.25 here, and we will have a parallel line here. So, the points are signified as this is the x direction here. So, A is the point, B is the point, C is the point here, D is the point here. This is origin, it is just chosen, and your length points are chosen as 1, 2, this is 3, this is 4 here. So, we are just finding this length of the sides B4 and C4, since both are equal there. To find this one, if you just consider like x square plus y square, this equals to, it is just given 0.25, and at this line if you just consider x equals to 0.25, it is just given here x coordinate, we have to find y coordinate at that point. So, that is why you can just consider y square, this equals to 0.25 minus 0.25 square there. So, which is nothing but 0.25 minus 0.0625. So, which is just given as 0.1875. If you will take this square root of this one, then we can just find 0.433. So, that is why if you will just define here C4, C4 is nothing but this distance is like 0.25 here. So, 0.433 minus 0.25, the remaining part it is just given as 0.183 here. So, this is nothing but B4 equals to also 0.183, and the value of the function f of x y, this is just given as like a 4 into mod x plus y at the mesh point 1, 2, 3, 4 here. If you just see here, so 1 just take the point as a 0, 0 there. So, if you just point 0 here, so this will just take the 0 value there. So, f1 is 0, and if you go for like f2 point here, f2 is nothing but x equals to 0.25 here. So, if you put here 4 into 0.25, y is 0. So, this will just take like 4 by 2.4, sorry 4 into 0.25, that is nothing but 1 by 4. So, that is why it is 1, and f3 point if you just go here, so this is nothing but x coordinate is 0 here, but y coordinate equals to 0.25. So, that is nothing but f3 equals to 1.0, and for f4 point if you will just see, so this is nothing but this point here. So, that is why this coordinate if you will just take here. So, 4 into if you just see here, x point is like 0.25 plus 0.25. So, that is nothing but 0.5 there. So, 4 by into 1 by 2. So, that is why this is just taking 2.0. So, if you will just go for this derivative condition which is defined at along the x axis here. So, we can just find that del u by del y, that is nothing but this last point which is defined as u4. So, for this derivative condition, if you just see in the picture here, we have just defined a like a fictitious domain there. So, this fictitious domain we are just giving this w as the west coordinate here, and east part it is just written as e here. So, for this if you will just take this like difference of u4 minus ue by 2h or the length here. So, then we can just obtain this derivative at this point. So, if you will just go like del u by del y, this can be written in the form of u4 minus ue by 2 del y. This can be written also as u3 minus uw by 2 del y at the point. If you just see, this is the value at the point 2 and this is the value at the point 1 there. This equals to 0 there. So, that is why u4 equals to ue and u3 equals to uw. So, this is at point 2, this is at point 1. And if you just discretize this partial differential equation at various mesh points using Gauss-Seidel method, then we can just get that point 1. If you just see, point 1 means we can just consider like q is the previous point there, and 2 is the secondary point there. So, if you use these points at different levels, so then we can just find, since our domain, if you just see, so the domain is defined in this form here. So, if you just see here, this is nothing but your point 1 here, this is the point 2 here, this is the point A here, and this is the point Q here. So, if you will just take the point of discretization as 1 here, so we can find UQ minus 2U1, and this is minus 2 point here. So, sorry, this is plus 2 point here. So, that is why we can just write this discretized equation as in the form U I plus 1 j minus 2 U I j plus U I minus 1 j by h square for del square u by del x square term. And similarly, we can just write del square u by del y square equals to u I j plus 1 minus 2 u I j plus u I j minus 1 by h square here. So, that is why if you will just combinedly write this equation. So, at the first point, if you will just see at point 1, so your values, it can be taken as uq plus u2 minus 4 u1 plus, if you will just see here, this point is nothing but it is considered as a third point here, this is nothing but fourth point. So, that is why this difference minus this difference we will just take, this is nothing but uw. So, that is why it is just considered as u3 plus uw, this equals to h square f1 there. And if you will just consider the symmetricity condition here, that is nothing but you can just consider uq, if you just see here, uq is nothing but u2 point here, and uw is nothing but u3 point here. So, it can be doubled there itself. So, that is why we have just written uq plus, we are just considering u2. So, that is why 2 u2 we can just consider, and this u3 and uw, it can be considered, since symmetricity it is there. So, that is why you can just consider this is as 2 u3 here. So, h square f1. So, at point 1 we are just obtaining this f function as 0 there. So, that is why if you will just take common here a minus also, then we can just write 4 u1 minus 2 u2 minus 2 u3 equals to 0. So, again if you will just take 2 common, so we can just write 2 u1 minus u2 minus u3 equals to 0 there. Similarly, at point 2, if you will just calculate here, so it can just consider point 1, point A, and it can consider point 4, and it can consider point E here. So, that is why it can be written as UA plus U1 minus 2 U2 plus U4 minus 2 U2 plus UE, this equals to h square f2. Since f2 value it is just considered as 1 here, so that is why we can just consider 0.25 square. So, that is nothing but 0.0625. And if you will just put all these values here, since along this boundary it is just defined this value u equals to 1 there itself. So, that is why it is considered as ua equals to 1, and u1 is there minus 4 u2. So, ue equals to u4. So, that is why this is 2 u4 it is just coming. So, this is the equation here. Similarly, if you will just find this point at 3, so you can just write that as up, since p is the point along this previous plane. So, that is why up plus u4 minus 4 u3 plus u1 plus ud, this equals to h square f3 here. So, then if you just put all these values here up equals to u4 symmetricity. So, u4 plus u4 minus 4 e3 plus u1 ud along the boundary, it is just defined as u equals to 1 there. So, that is why this value can be written in the form of 2 u4 minus 4 u3 plus u1 equals to minus 0.9375 here. So, since this space is defined is in irregular domain shape here, grid sizes are not uniform. So, we can just use this formula for like derivatives of unequispaced points. So, if you will just follow like numerical methods lecture of ours, then you can just find that one. So, especially in this case we are just using like two different points. Suppose if x0 is the point there and h1 is the first grid length here, then h2 is the second grid space here. So, like two different points I am just writing here. So, x1 can be written as like x0 plus h1 and x2 can be written as like x0 plus h1 plus h2. Then if you just take Taylor series expansion at these 2 points, like f of x1 can be written in the form of f of x0 plus h1, which can be written as f of x0 plus h1 f dash of x0 plus h1 square f double dash of x0 by 2 factorial. So, plus rest of the points. Similarly, if you will just expand the Taylor series expansion at this point here, then we can just write f of x2, this is nothing but f of x0 plus h1 plus h2, which can be written as f of x0 plus h1 plus h2 f dash of x0 plus h1 plus h2 whole square by 2 factorial f double dash of x0 plus rest of the points. So, if you will just eliminate here f dash of x0 from both these equations, so then we can just obtain this formula in this form here, neglecting these higher powers of h1 and h2. And especially this second order differential formula, it is just written as 2 by h1 h2 into h1 plus h2, h1 f of x minus h2 minus h1 plus h2 f of x plus h2 f of x plus h1 here. So, for unequal intervals, the discretized equation is like 2 by 0.25 into 0.183 into 0.25 plus 0.183 into 0.183 u3 minus 0.25 plus 0.183 u4 here plus 0.25 ub. So, this is h2, it is just there, plus 2 by 0.25 into 0.183 into 0.25 plus 0.183. Since we are just considering the second order derivative for like first del square u by del x square, then we are just writing for del square u by del y square. So, this is nothing but f4 there. So, if we will put these values, then final form we are just obtaining this linear equation here. And if you will just consider these two equations 4 and 5, so both these equations especially you can just find these are like 2 u4 it remains same. So, u1 remains same. So, that is why these coefficients if you will just compare here u2 equals to u3 we are just getting. And if you will just use this one in a first equation, we can just get u1 equals to u2 equals to u3 there. And if you just simplify equation 4 and 6, we can just obtain 3u3 minus 2u4, this is 0.9375. And then especially if you just solve these equations simultaneously, we can just get u1 equals to u2, that is nothing but u3, this will just give you 0.9657 and u4 equals to 0.9798 here. Thank you for listening this lecture.